Section 14.3, Concentration and Rate. Continuing to talk about Chapter 14, Chemical Kinetics. Make sure you've got this rate, this notes sheet out in front of you, and you're able to write down the notes. And you might want to have a calculator and a extra sheet of paper out next to you as well to take some extra notes and show a little mathematics. One of the ways of studying the effect of concentration on reaction rate is to determine the way in which the rate at the beginning of a reaction depends on starting concentrations. This is known as the initial rate of a reaction. We'll now look at the way in which the rate at the beginning of the reaction, known as the initial rate, depends on the starting concentrations of reactants. So in general, when we study how concentration can affect rate, for a reaction A plus B goes to C, we can write an expression or a mathematical equation that's called the rate law expression or the rate law equation. And the rate law expression or rate law equation for any given reaction generally looks like this. The word rate, you write the word rate, is equal to some constant k, a small letter k, a lowercase k, which is known as the rate constant, times the concentration of the first reactant, in this case it's A, times the concentration of the second reactant, B, and this reactant concentration A and B are both raised to some power. We'll call it power X, and we'll call this one power Y. And these powers right here are known as the order of the reactant. Now, these exponents right here are going to be a huge focus of what we look on during this video cast, and so you have to kind of get the word exponent and order to mean the same thing in your brain, because that's the terminology that's used. And the only way you can know these exponents or these orders is by experimentally determining them. A lot of people get this confused and say, doesn't it have something to do with the coefficients in front of the balanced chemical equation? The answer to that is no, not at all, not at all. The concentrations right here, remember these brackets mean concentration in molarity, is the initial or the starting concentrations of reactant A and reactant B. And as I alluded to before, this K right here stands for something called the rate constant. The rate constant, and it's constant for, or it's the same type of number for any concentration A or any concentration B in that particular reactant. Now, of course, the rate depends on all of these things. Rate depends on all of these things. And you can write a rate expression like this for any reaction as long as it is at one constant temperature. And the rate will change, of course, if you vary the temperature, which we'll talk about later in section 14.5. So what is a rate law? Well, a rate law is a mathematical expression or a math equation that relates a rate constant, concentrations, and their exponents or orders to one another. What is the name of the quantity K in any rate law? Well, I've got it written right up here. K is called the rate constant. Notice it's a lowercase letter K. We'll actually talk about an uppercase letter K in chapter 15, so it's very important to keep it straight in your mind that the lowercase letter K is for the rate. And the rate expression like this is always written for the reaction going from left to right, from A plus B goes to some products. It's always written from left to right. If you were to write the reaction rate expression for a reverse of the reaction, you'd usually put the rate constant like this and put a little F down here to mean forward, meaning left to right. Or if it was going backwards, you'd put K with a little R down below it, meaning reverse. And you'll see that sometimes, but it's not used in this video cast. It's used later on in the chapter. So it's always written for the left to right, like we read reaction. True or false, a rate law can always be determined directly from the balanced chemical equation. I can't write false any bigger. Can't write false any bigger. You can never for sure determine what the rate expression is or the rate equation is from the balanced chemical equation. Now there is a way to determine it from some equations, but hang on to that thought until the very last part of the chapter. Okay? And you can never find it from the overall balanced chemical equation unless they give you lots more information. So here's a question. The experimentally determined rate law for the reaction 2NO plus 2H2 goes to N2 plus 2H2O is rate is equal to K NO2 to the second times H2. What are the reaction orders in this rate law? Well, remember the word order means exponent. And get that into your brain right now, because order and exponent are usually used interchangeably in this chapter. Mostly we use the word order. And so if you look, NO is raised to the second power, so you say it's of second order. And H2 doesn't have a number written above it. And remember, if there's ever a number written and it doesn't have an exponent, it's to the first power. And so we say it's to the first order. This is a second order reaction. This is a first order reactant. Now, you'll also hear that there is what's called an overall order for a reaction. And this is really simple to get. Just take a look at the rate expression or the rate equation like this. Look at the exponents. This one's a 2, this one's a 1. And if there were more reactants with more exponents, you'd take and you simply add them together. And 2 plus 1 in this case is equal to 3. And so the overall order of the reaction is third order. This is overall now for the reaction. Notice that in terms of NO reactant, it's second order. In terms of H2 reactant, it's first order. Question B, does doubling the concentration of NO have the same effect on the rate as doubling the concentration of H2? Well, let's just do a little simple math and let's see what would happen. The equation, remember, is rate equals some constant K, NO to the second power, H2 to the first power. And let's just give it some pretend numbers. Let's pretend that K is equal to 1, and let's say that NO is 2 and H2 is 2 for a concentration, okay? The rate for this, if NO is 2 and H2 is 2, would be 2 squared, which is 4 times 2, which would be 8. Now let's say that we double NO. Now it's a concentration of 4. Keeping K the same, because remember the rate constant is the same no matter what the concentrations are. The only time it changes is with temperature. Now we have 4 squared, which is 16 times 2, 32. Now what happens if we double H? So we have 4 here to the first power, but we leave N2 the same. Now what would be the rate of the reaction? 2 times 2 is 4, times 4 is 16. So answering the question, does doubling the concentration of NO have the same effect as doubling the concentration of H2? It doesn't look like it, because here I doubled NO, and look at that, it went to 32 from normally a rate of 8. Here I doubled H2, and it went to 16 from a normal concentration of 8. And so you can see that by having a square or a second order reactant versus a first order reactant, you can speed up the reaction considerably more, or have a much faster rate by doubling or increasing the one that has a square to it, which mathematically probably makes sense to a lot of you. On the next page, there's a nice colorful picture. Well, it's probably not colorful in your handout, but it is colorful on page number 584 if you have the 10th edition of the textbook. Or you can just look at my colors and you can write in what the colors are on your black and white version. It says, consider the reaction A plus B goes to C, for which the rate is equal to K equals A to the first power, B to the second. Each of the following boxes represents a reaction mixture in which A as red spheres, I'll just label these A here in case you want to label yours as well, because yours probably aren't in color, and B is purple ones. So I'll label all the A ones here that are red, and you can go ahead and label them on your document as well. And it says, rank these mixtures in increasing rates of reaction. Rank these mixtures in increasing rates of reaction. Well, we know that the rate expression right up here is rate is equal to K, A to the first, B to the second. And as we saw in our last question, the one that is squared, or to the second order, of course, is going to make a larger difference in the rate than the one that's to the first order. But let's go through and let's calculate the rates just to find out for each one of them. So for box number 1, I'm just going to slide this up and have a second piece of paper here to do the calculations a little bit under. For box number 1, we have rate is equal to some constant K. I'm going to call K1 again just to make it easy. Okay, that's K. And then A, there's 1, 2, 3, 4, 5 of them, and that's to the first power. And B, there's 1, 2, 3, 4, 5 of those as well, and that's to the second power. So 5 squared is 25 times 5, so we have a rate of approximately 125 times the rate constant K, which I just called 1. For box number 2, we have a rate equals, and I'm going to put 1 in for K again, and we have 1, 2, 3, 4, 5, 6, 7 of the A's to the first power, and we have 1, 2, 3 of the B's, and we've got to raise that to the second power. So 3 squared is 9 times 7 is 63, so 63 times K, which I just called 1. For box number 3, if we wanted to find out the rate, put in K, I'll call it 1, and we have 1, 2, 3 of the A's to the first power, and we have 1, 2, 3, 4, 5, 6, 7 of the B's, which we have to raise to the second power. 7 times 7 is 49. Times 3 is about 147 times K, which is just, I called 1. So which one turns out to be the fastest? Well, the largest number is the fastest. And if we were using units here, we'd have molarities and molarity squareds right here. And this would be units that would give us a rate of molarity per unit time. And depending on what our time was, from our rate constant, it could be molarity per second, per minute, per hour, whatever it is. But anyway, this is going to have the fastest or the largest magnitude. So if we rank them, we say that box 3 is the highest. And then box 1, of course, is the second highest. And then box 2 would be the slowest. So from fastest to slowest, we can see that the one that has the most concentration of B's turns out to be the one that reacts the quickest, which kind of makes sense. Because this one is squared in the rate expression, or in the rate equation. Now, when we deal with substances, we can't go in and count the number of molecules, but we can count moles of molecules, and so that's why we deal with molarities or concentrations rather than just individual molecules. But this gives you an idea on a molecular scale what we're looking at. Second question says, assume rate is equal to K times A times B. Rank the mixtures represented in this sample exercise in order of increasing rate. Well, now if they were the same, just A times B, then we'd have to take a look at each one individually, and we could just put in the numbers and do the same kind of math that we did before. And for number 1, we'd end up with rate is equal to K, and it'd be 5 times 5, because there are 5 A's and 5 of the B's, so that'd be 25. And then in B right here, we'd have 1, 2, 3, 4, 5, 6, 7, or I'm sorry, in box number 2 I called it B. 7 times 3, 7 times 3 is 21. And then in box number 3, we'd have 3 times 7. Once again, 3 of the A's times 7, so that'd be 21 as well. So you can see that number 2 and number 3 would have the same rate, and box number 1 would be the largest. So if we went from increasing reaction rate, we'd have to say 3, which is equal to 2, which is less than 1. Next set of questions. We're given 3 equations and asked some questions about them. And we're given the rate expressions for each one, or the rate equations for each one. And it says, what are the overall reaction orders for the reactions described in equation 1 and equation 2? So in equation 1, here's our rate expression. You'll notice that it's only dependent on N2O5, this reactant, and it's raised to the first power. So we say that for equation 1, the reaction order has an overall order of, or exponent of 1. In reaction 2, you can see that CHCl3 is raised to the first power, and Cl2 is raised to the 1/2 power. Now, to find the overall reaction order, you take the 2 powers and add them, and 1 plus 1/2 is 1/2. So the overall order for equation 1 is 1, for equation 2 is 1/2. Notice, once again, it asked for the overall reaction order, and to get the overall reaction order, you simply add the exponent. Second says, what are the units for the rate constant for the rate law equation 1? Okay, well, it tells us that the rate in equation 1 is equal to some constant K times the concentration of N2O5. Well, if we know the concentration is measured in terms of molarity, we can put in a capital M for molarity. K is the thing we want to know the units for. And a rate is always measured in some concentration per unit time. So let's call it molarity divided by, and pick a unit of time. Let's choose seconds, just because that's easy. Molarity per second. Now we want to solve for K, so I'm going to end up dividing both sides of the equation by m, or I could say multiplying by 1 over m. That's the same thing. And then the m's will cancel, or the molarities will cancel on this side, and it turns out that the m's also cancel on this side, and I'm left with 1 over seconds. And like I said before, the book in this chapter really likes to use negative exponents, so you can write it as either 1 over m or as s to the negative 1 power. And so K would be in units of per time, or 1 over seconds, since we chose seconds as our time. Determining the units for the rate constant is a really popular question on a test coming near you in May. What is the reaction order for the reactant H2 in equation 3? So back up here to equation 3, we look at reactant H2 and we look to its exponent right here, and it has an exponent of 1, so we say that the reaction order for H2 is 1. The overall reaction order would be exponent of H2 plus the exponent of I2, which would be 2, of course, 1 plus 1. And lastly, what are the units for the rate constant in equation 3? The rate constant right here is K, and so we need to solve for that animal. We've got an expression that says rate is equal to some constant K, H2 times I2. And we're going to solve for K. But let's put some units in. We know that these are both measured in molarity. So it's molarity times molarity times some constant K that we don't know the units for yet. And rate, of course, is measured in concentration per unit time. And once again, let's just choose seconds, because seconds is an easy unit of time to work with. Now I'm going to have to divide this side of the equation by molarity times molarity, and do the same thing to this side, except I'm going to write it like this. I'm going to write it as 1 over molarity to the second power, because m times m is m squared. Notice these guys drop out. I've got K alone. the molarity drops out here, and I lose one of my molarities here. And so the units of K turn out to be 1 over molarity times seconds, or, like I said, the book likes to do it, likes to write it with negative exponents. It would be equal to molarity to the -1 times seconds to the -1. Get used to things as 1 over being just with negative exponents. Being able to solve for the rate constants units are a critical component a number of times in this chapter. Going on to the next page. Now, as we said before, you can't determine the rate of an experiment or of a process simply by looking at the chemical reaction. You need to experimentally determine it. And so in these next two questions, we're going to look at some experimental data. We're going to look at some experimental data and have the experimental data help us determine what the rate expression is and what the exponents or the orders are for the reactants. Question number 1 says the initial rate of a reaction A plus B goes to C was measured for several different concentrations, starting concentrations of A and B, and the results are below. Using the data to determine the rate law for the reaction, that's the equation, the rate equation, the magnitude of the rate constant, that means the numerical value. That's what magnitude means, numerical value. And lastly, the rate of the reaction when A is equal to and B is equal to. That means once we have the rate expression, we'll plug these numbers in and actually get a physical number for the rate. Usually it also asks, and we're going to see if we can solve for this, also for the units of the rate constant, just like we did in the last sample problems. Now, there are a couple ways to go about this. The first one is just a straight mathematical way, and I'll show you how to do that. The second way is to just kind of look at how the rates change versus one another for different experiments, and from that you can deduce what the exponents or the orders of the reactants would be. So we know that the rate expression is going to take on a equation that looks like this. Rate is equal to some constant K, remember it's a small letter K, times the concentration of A to some power, I'll call it X, times the concentration of B, let's call it to the power of Y, because those are our reactants right here, A and B. I don't know whether X or Y is going to equal 0, 1, 2, 1/2, 3/2, 4, -1/2. I don't know for sure what it's going to be. My job is going to be to find out what this X is and what this Y is. And I need to be able to experimentally determine those. The way that I'm going to do it is I'm going to compare two rates. I'm going to compare rate 2 to rate 1. And this is the straight mathematical way to do it. Once you see this way, you might be able to deduce it without actually doing all the math. I'm going to say that rate expression for equation number 2 compared to, and when I use the words compared to, I mean divided by. To the rate expression for equation number 1. Okay? Now, the rate expression for each one is going to be the same, where rate for experiment 2 is equal to some constant K times the concentration of A, which happens to be 0.1 molar. I got that from right here. Raised to some power, I'll call it X, times the concentration of B, which is 0.2 molar, raised to some power, I'll call it Y. This is equal to, this is being compared to experiment 1, who has the same rate constant K, but the concentration of A in this case was 0.1 as well, and the concentration of B in this case was 0.1, and I'll raise that to power Y. Now you can see that several things are going to cancel out. The K's are going to go away because they're the same. The 0.1 raised to the power X's are going to go away. And I end up with 0.2 divided by 0.1 to the power of Y. And if you remember your exponents from math class, these two Y's actually are the same thing. And when I divide 0.2 divided by 0.1, I end up with 2 raised to some power Y is equal to the rate of 2 divided by the rate of 1. The rate of 2 is 4 times 10 to the negative 5th molarity per second, divided by the rate of 1, which is 4 times 10 to the negative 5th. I'm sorry, I meant negative 5th. Whoa, those two numbers are the same. Two numbers that are the same is equal to 1. So I end up with the mathematical equation 2 to the y power is equal to 1. What exponent would y have to be to make it so 2 is equal to 1? Well, remember from your mathematics class that anything raised to the 0 power is always equal to 1. So that means y in this case must be equal to 0. Is that a legal number for an exponent? Sure, it's possible. It's possible. It just means that that's going to turn out to be 1. And in case of rates, the B concentration is always going to be to the 0 power, and therefore it's not really even going to be in the rate expression. This whole thing is just going to be 1, with meaning that B isn't going to have very much of an effect on the rate at all. So we found the first exponent or order, that's 0. And now we're going to compare two more rates. And when we compare two other rates, what we want to do is we want to select ones that are going to cancel the y's out. Or since we know that y is equal to 0, I guess it doesn't matter which ones we choose, because they're always going to turn out to be 1 anyway. And then we want to find a place where x is going to change. And we'll see how the rate changes as x changes. So in this case, let's compare the rate of 3 right here to the rate of 1. And we can see in this case that B's rate doesn't change at all. Now we could have done this one first, we just chose not to. So let's compare rate 3 to rate 1. And in this case, on the rates again, rate 3 is going to equal some constant k, where A is equal to 0.2 raised to some power x, times the concentration of B, which is 0.1 raised to some power y. Well, I already know what y is. It's 0, but I'm not going to put it in there right now. Rate 1 is equal to some constant k, and in this case, rate 1 is 0.1 raised to some power x, and rate 2 is equal to 0.1 again raised to some power y. Now I know that y's are 0, so it doesn't matter because 0.1 to the y and 0.1 to the y, they're all both going to cancel out. The k's cancel out. And if I compare rate 3 to rate 1, rate 3 is 16 times 10 to the negative 5th, and rate 1 is 4 times 10 to the negative 5th. Whoa, the negative 5ths go away. Very nice. 16 divided by 4 is 4, it looks like. So I have 0.2 divided by 0.1 to the x power, and so I could write it this way. 0.2 divided by 0.1 once again is 2, and it has to be raised to the x power, and it has to equal 4 because that's what these rates end up equaling. 16 divided by 4 is 4. What must the exponent x be to make 2 equal to 4? Well, of course, 2 to the second power is 4, so that means x has to be equal to 2. I've now found the orders of the reactants, and this allows me to write the full rate expression with the powers, also known as the orders, in the equation. And so to answer letter A, the rate law for the equation is rate is equal to some constant k, A to the second power, B to the 0 power. And you don't have to write B in there if you don't want, because B to the 0 power, of course, is 1, and you don't have to write the number 1 in there if you don't want, but I wrote it in there for completion right now. The second question, letter B, said, what is the magnitude of the rate constant? Now we want to find a numerical value for K. And to do that, just pick any experiment, 1, 2, 3, or 4. It doesn't matter which one, and put the numbers in. Put the numbers in. Because K is going to be constant, the same for any one of them. You can just pick one. Let's pick the first experiment just because it's easy. So the rate for experiment 1 was 4 times 10 to the negative 5th, and this is equal to some constant K times the concentration of A, which is 0.1, and let's raise that to the second power, times the concentration of B, which is also 0.1, and we're going to raise that to the 0 power. Anything to the 0 power is 1, so that goes away. 0.1 squared, and then I'm going to have to divide both sides by this 0.1 squared to find K. So K is equal to 4 times 10 to the negative 5th divided by my 0.1 squared. And that turns out to be 0.004, or I could write it as 4 times 10 to the negative third for my units of K. My magnitude of K. Now to find the units, I should put the values in here for the concentrations, molarity and molarity, and then molarity per second for my initial rates. I'm just going to write it on the back of another piece of paper here. So I've got a little bit more room. Slide this up. And putting the units in now. Rate, remember, is measured in molarity per second. This is equal to some constant K. And then this was measured in molarity, and letter A was squared, and then letter B, of course, was to the 0 power, and that was measured in molarity, and that's to the 0 power, so that's 1 that's going to go away. Divide both sides by molarity squared, or multiply by 1 over molarity squared. One of them goes away on the bottom, and the top one goes away, and so K ends up with units of 1 over molarity times seconds, or molarity to the negative 1, seconds to the negative 1. And so up here on my units, or on my K, 4 times 10 to the negative third is the magnitude. Molarity to the negative 1, seconds to the negative 1 is my units for that 4 times 10 to the negative third K. Lastly, letter C said the rate of the reaction when A is equal to 0.05 and B is equal to 0.1. So now that I know the rate expression and the magnitude in units of the rate constant, I can plug that right in. I'm just going to slide this up here so that I can put the numerical values in. I know that rate expression is equal to some constant K, A to the second power, B to the 0 power, and so I can take these numbers and plunk them in. K I solved for down below in letter B, and that was 4 times 10 to the negative third. 4 times 10 to the negative third, and the units on that were molarity negative 1, seconds negative 1. And then A squared was 0.05, they said to put in there. Oh, and the units on that are molarity. And then that has to be to the second power, because remember it's A to the second power. And then B is not going to make a difference because it's to the 0 power, but I'll still put the number in there. It's 0.1 molar, and that is all to the 0 power. And of course that's just going to go away, and that's going to be 1. And then I need to square the 0.05 and multiply it by the 4 times 10 to the negative third. And if I do this, I end up with 1.6 times 10 to the negative fourth. And the units on this, these units, I've got molarity squared right here, and my units on the rate constant are molarity negative 1, seconds negative 1. So one of the molarities is going to go away. And then I'll have molarity per second as my units, because the seconds, of course, since it has a negative 1 exponent, means it's 1 over S. Or I could write it as molarity times seconds to the negative 1. That would be okay as well. One more sample problem that's similar. I'm going to show you a second way now that you can determine the rate expression by maybe a little less mathematical means. And this says the following data were measured for the reaction of nitric oxide with hydrogen, and it gives us an expression, or I'm sorry, a chemical equation, and then it gives us a bunch of data. Experiment 1, 2, 3, and 1, 2, 3, some concentrations, and then some initial rates. And it says determine the rate law for the reaction, calculate the rate constant. Of course, it wants it with units, and then calculate the rate. It's the same exact question. The only thing that's changing now is it's a different equation. That's all. So let's see if we can just look at how the rates change with concentration. Notice here the concentration from experiment 1 to experiment 2 in NO don't change. So the only thing that's affecting the rate of the reaction now is the concentration of H2. Notice what happens from 1 to 2. We're doubling H2. If you double H2, what happens to the initial rate? It goes from 1.23, just ignore the exponents for right now because they're both 10 to the negative 3, and it goes from 2 to 2.46. Well, what's double of 1.23? Well, 2.46, right? So if you double the concentration here, you double the initial rate. Well, that turns out to be analogous to an exponent or an order of 1, a first order reaction. So that means that the order with respect to H2 is going to have to be 1, or an exponent of 1. If you double the concentration and you double the rate, that means it's to the first power. Now let's take a look at a second consequence. Let's look at experiments 1 and experiments 3. Well, let's just write down what we know so far first. We know that the rate expression is going to be rate is equal to some constant K, concentration of NO to some power X times the concentration of H2 to some power Y. And we already determined just by looking at this that if you double the rate, you double the concentration, or vice versa. Double the concentration, you double the rate. That means that H2 is to the first power. So instead of writing Y in there, I could write in a 1. Okay? And then NO is to some power X. We don't know, but let's take a look at another reaction, another set of reactions, 1 and 3, and see if we can figure out what X is. Let's look at 1 to 3. From 1 to 3, the concentration of NO doubles. Concentration of NO doubles. From 1 to 3, the concentration of H2 remains the same. So the only thing affecting the rates now is the concentration of NO. If I double the concentration, do I double the rate? Oh no, that's not quite double. That's a little bit more, isn't it? As a matter of fact, if you do a little mathematics of this, 1.23, and you multiply it by 4, you get 4.9. Notice they're both 10 to the negative third, which you can kind of ignore right now because since they're both the same, you can just look at the magnitude of the first number. And so, in other words, I've had a 4-fold increasing of the rate. When you do that, the order is said to be squared, or second order. Second order. If you want to see another example of this, you just look up here at our first experiment. You can see that the same thing happened here when we doubled the concentration of A from 1 to 3, and we held B constant at 0.1. What happened to the rate? It went from 4 times 10 to the negative fifth to 16 times 10 to the negative fifth. Well, we didn't double it, we squared it, right? And when you square it, that means it's the second order. And so that means X right here has to be to the second power. Now, you may encounter other exponents other than 1 and 2, or 0, which we encountered up here. But these are the most prominent, 0, 1, and 2, and we'll focus on those a lot during this chapter. Although on past exams, there have been some 1/2s, which would be square rooted, of course, and there could be some other strange numbers here as well for the orders. But just by examination, we can determine the orders of the reactant, and we don't have to do all this comparing right here. It's nice to be able to fall back and do this comparing if needed, but you don't necessarily have to. So just by taking a look at these, we've come up that the rate expression is rate equals some constant K, NO to the second power, and then H2 is to the first power. So we can say that the overall order of the reaction is 2 plus 1, or 3. The H2 is to the first power, and NO is to the second power. That's letter A. Letter B says calculate the rate constant. Well, just pick an experiment. Let's pick experiment number 1 once again. Rate is 1.23 times 10 to the negative third, and the units on that are molarity per second. This is equal to some constant K times NO, which is 0.1 molar in this case, and it has to be squared, times H2, which happens to be 0.1 molar again in this case. I'll put a capital M in there, and that's to the first power. Okay, solving for this. Divide both sides by 0.1 times 0.1, which is 0.01. And then also, I'm going to have to divide both sides by molarity to, whoops, I forgot to square this. 0.1 squared is 0.01 times another 0.1, which is 0.001 my bad, square this guy, and then multiply by 0.1 again. Okay, and notice this is going to be molarity to the second power and molarity to the first power, which means I'm going to have to divide it by molarity cubed. And dividing this side, remember once again, it's actually 0.001. I forgot to square this over here, now I did. And this is molarity to the third power as well. Now doing this little bit of math right here, I believe I end up with, let's see, if I plug this into the calculator, I end up with the magnitude of this being 1.2. And my units, this is kind of the fun part right now. Remember, this is a complex fraction with molarity per second per molarity to the third power. I can take this one and write it over 1, and then what I do is invert this and multiply times the m. Invert and multiply means that I'll have molarity per second times 1 over molarity cubed. Okay, one of these goes away, and I end up with molarity squared, and this goes away. So I end up with units of 1.2 seconds to the -1, molarity to the -2. That's my units and magnitude of my rate constant. Units and magnitude of my rate constant. Okay, and then lastly, letter C. Calculate the rate when NO is equal to and when H2 is equal to. Now we just plug it into the rate expression that we already know. And the rate expression is equal to K, which we just solved for, 1.2 seconds to the -1, molarity to the -2, times NO, which is 0.05. 0.05 molar, and that's got to be to the second power because NO is to the second power right here, times the concentration of H2, which is 0.1, and that's raised to the first power. Whoops, that's molarity to the first power. Multiply these guys together, and notice my units cancel where the molarity squared will go with the molarity squared, and I'm left with molarity over seconds, which is units for rate, molarities per seconds. And if you're not used to checking units all the time with every single problem, get really used to it during this chapter, because you always want to know what you're going to end up with, because the units become super duper critical lots of times. And if you do this mathematics on your calculator, I believe you end up with 4.5 times 10 to the -4th. 4.5 times 10 to the -4th molarity times seconds. That concludes determination of the rate law from initial rates.